Hi, everyone. We'll go ahead and get started for the M-Cube seminar. I'm pleased to welcome Ben Barr. Ben is a postdoc at Woods Hole Oceanographic Institution, where he studies air-sea interactions in tropical and extratropical cyclones over the Atlantic Ocean. His projects at Woods Hole include developing constraints for high wind air-sea heat fluxes with sea spray using in situ data sets and exploring wave-based air-sea flux model physics and coupled atmosphere wave ocean model simulations. Prior to coming to Woods Hole, Ben obtained his PhD in atmospheric sciences from the University of Washington, where he developed a new Seastate-Dependent sea spray heat flux parameterization and explored the impacts of sea spray on hurricanes and coupled regional model simulations. Ben is broadly interested in air-sea interactions at all scales, but he's particularly interested in the high wind regime in winter storms and hurricanes, which is particularly relevant today, I guess, where complex non-equilibrium sea states, copious wave breaking, sea spray and bubble generation, and coastal injection push the limits of scientific understanding, modeling, and observational capabilities. Welcome.
All right. Thanks so much, Hugh. Appreciate it. Hi, everybody. I'm very happy to be here. As you said, my name is Ben Barr. I'm a postdoc at WHOI. I'm going to be talking today about sea-state-dependent air-sea heat fluxes with sea spray and high winds, looking at physical processes, models, and observations. Very grateful for the collaboration with my PhD advisor, Shui Chen, with Chris Farrell from NOAA, and from my team at WHOI, which is Hyode Seo, Cesar Savage, Caroline Clayson, and Jim Edson. So we're going to get to sea spray, but first I want to talk sort of broadly about high wind air-sea fluxes as a key element in the Earth system. We generally define the high wind regime as corresponding to 10-meter wind speeds greater than about 20 meters per second. This regime has a huge presence in extreme weather events. So most famously, probably, hurricane intensification. We've got one of those going on right now in the Gulf of Mexico. This is a satellite loop of, of Hurricane Lee from last year, intensifying from Category 1 to Category 4 in about 12 hours. Record-breaking intensification. This intensification is governed by air-sea interaction. So momentum fluxes from the surface modify the angular momentum moving in towards the core of the storm, and the air-sea heat fluxes give the enthalpy that's released in convection to drive the intensification. Extratropical cyclones also have a large presence of air-sea interaction and high winds. This is a bomb cyclone from January of last year approaching the west coast of the United States. Air-sea interaction, air-sea heat fluxes, and momentum fluxes change the boundary layer structure, affecting the inflow and convergence towards the center of these storms. And they also provide the latent heat whose release can modulate the developing baroclinic instability. While we generally tend to think of high-impact weather systems as kind of isolated incidents, if we take a step back and look broadly, we can see an imprint of high winds on a global scale. This is 10-meter wind speed from quarter-degree CCMP product. This is the month of August in 2018. High winds are shown in orange with a black outline. And we can see that there's almost always high winds somewhere on the Earth. We can occasionally catch a glimpse of a tropical cyclone in the summer hemisphere, which is the northern here. But there's a huge presence of high winds. Of high winds almost all the time in the mid-latitude cyclones in the winter hemisphere. So we can then begin to wonder about high winds as kind of these global impacts of these fluxes. So we need to understand these fluxes and high winds. We need to parameterize them. This is the air-sea interface in low winds. As you can see, it's not flat, so it's covered in a surface wave field. These waves provide the physical mediation of momentum and heat from the atmosphere between the atmosphere and the ocean. In low and moderate winds, this flux is dominated in the atmosphere mostly by the turbulent motion of eddies, moving momentum and energy from the free atmosphere down to the surface. And we define the, I'm having trouble with this laser pointer. So we define the wind stress or the momentum flux, the sensible heat flux associated with changes in potential temperature, and the latent heat flux associated with changes in moisture as the net result of these covariant fluxes of velocity, temperature, and humidity. We usually model these using Monod-Nabokov similarity theory, which gives us dependencies on 10-meter wind speed, air-sea temperature difference, air-sea humidity difference. There's also these terms, bracketed terms, that account for the sort of structure of the turbulence, the characteristics of the turbulence. and how effective it is at moving these fields. It is common to kind of group the bracketed terms into coefficients for drag and heat, which is commonly used in models. This approach works fairly well at low and moderate winds when transfer is dominated by the motion of turbulent eddies, but at high winds, we start to see the appearance of processes that push these physics into new realms. So here's footage from a sail drone a few years ago in Hurricane Sam. We can see just the enormous presence of waves with a wide range of heights and wavelengths. Everywhere these waves are breaking, injecting air and bubbles into the upper ocean and ejecting sea spray into the lower atmosphere. These new physical processes provide new pathways for the transfer of momentum, heat, gases, and aerosols that are not summarized or encapsulated by this bulk theory. So we then have to kind of start to think about high winds as corresponding to the appearance of new processes that we have to account for in order to make correct predictions. To summarize challenges in the high wind regime, we have, as we just saw, complex and unique processes: spray, bubbles, wave breaking, changes to wave state, airflow separation from waves. We have non-equilibrium sea states. So in low and moderate winds, oftentimes waves will be in equilibrium with winds, meaning that if you know the waves, or if you know the wind, you can predict the waves. They're correlated. In high winds, you often run into new physical processes in cases where that's violated. So transient wind forcing, fast-moving storms, propagation swell, bottom interactions cause sea states to behave, to kind of take on their own personality and to not become correlated with winds. High winds often occur in complex coupled systems, atmosphere, wave, ocean, and land. So for instance, this Hurricane Helene moving towards the coast, we want to predict storm surge for that, right? So we have to understand waves, ocean, atmosphere, land, and all these components together. From a practical point of view, it's very difficult to obtain long-term and simultaneous observations. The high wind regime is hostile to instruments and people. It's very hard to get these observations. And then finally, even if we get a handle on all this, we still have to distill all of this into into efficient parameterizations and coupling strategies that can be used in forecast models, often operating on a very quick cycle. So that's the challenges. That's a lot. We're not going to look at all that today. Today, we're just going to look at kind of a narrow slice of that, talking about air-sea heat fluxes with spray in sea state dependence and their effects on hurricanes. So we're just restricting our focus to heat fluxes, to this new process of sea spray, looking explicitly at its sea state dependence and how all that affects hurricanes. We're going to ask several science questions. First is, what do these fluxes even look like? We don't have good measurements, so if we try to use our best modeling physics in realistic hurricane conditions, what are these fluxes actually going to behave like? Next, how do these fluxes affect the storms? And then third, we have very limited observations, but can we actually deduce a presence of spray from currently available data sets? The approach that was a big part of my PhD was to develop a new parameterization for air-sea heat fluxes with spray, acknowledging the sea state dependence and incorporating sea state dependence. And we're characterizing that using output from coupled atmosphere wave ocean models. To address science question 2, we're putting this parameterization into the coupled model system and exercising it on hurricanes, exploring coupled interactions and the impacts on intensity and structure. And then finally, we're going to compare the new spray parameterization to a large data set of direct covariance flux measurements in high winds. Okay, so part 1, the fluxes themselves. How do they behave? How can we model them? Well, all this is made possible by coupled modeling, atmosphere, wave, ocean coupled modeling systems. The one we used for this work is the Unified Wave Interface coupled model that's developed and maintained by Shui Chen and her group at Washington. This is a coupled model that uses WRF for the atmosphere, which is run with 3 nested vortex following domains down to 1.3 kilometers horizontal resolution. It's coupled to the University of Miami wave model, which is a spectral wave model that's run at 4 kilometers horizontal resolution with 32 directional bins and 37 frequency bins. We use HICOM for the ocean at approximately 4 kilometers horizontal resolution. And this is coupled using the UN coupler, which is an ECMF coupler that has an exchange grid at a resolution of 1.3 kilometers and exchanges fields at 60 seconds frequency. So that's the coupled model that we're using. Now let's get into this parameterization and the physics that we're trying to address. The first process is sea spray generation, just the ejection of droplets into the near surface flow. Historically, this has been parameterized using wind speed only. It's been very difficult to get wave measurements and to incorporate wave physics into models, so wind-dependent parameterizations were the best option. A widely used model, is this one right here, which is due to Farrell et al. 1994. This is a plot of the sea spray generation function, which is droplet radius on the bottom and basically mass at that radius on the y-axis. So the production is very small at less than 10 micrometers, rises up to a peak around 100 micrometers, and then drops off. So we have the sort of relevant range is from 10 micrometers to a couple millimeters, with a peak around 200. And what we wanted to do when we were working with Chris at NOAA was to kind of update on a Seastate-based model that he'd been working on. So has a lot of terms, looks like this. It incorporates several wave dependencies, uses the wave energy dissipation flux, which is the net flux of energy from wave breaking into the ocean, uses significant wave height, dominant phase speed, and mean squared wave slope. All that gets baked into this right here. And it really kind of comes down to two terms that we're modeling here. We model the rate of formation of droplets, and we model the probability that they'll be ejected. So this rate of formation of droplets, droplets are assumed to be formed by the extraction of energy from this turbulent cascade that's under breaking waves. So as waves are breaking, turbulence randomly ejects droplets across a range of radii. And that produces curves that look a lot like this in blue. As wave dissipation increases, the production of spray increases. The next term, ejection, models how easily it is for turbulent gusts to entrain these droplets into the near surface flow. It's very easy to entrain droplets when the radius is small. As droplets get larger, this drops down because it's much harder for gusts to entrain droplets. As surface winds increase, it becomes easier to entrain these droplets, so we can get more large droplets at higher winds. When we put all this together, we get sea spray generation functions that look like this. So these kind of jointed curves are reproductions of the 1994 model, and these smooth curves are results from this new Seastate-based formulation. A couple of important characteristics. The wave-based model doesn't allow the size distribution to change. The magnitude just scales with wind speed. And this Seastate-based model allows both the magnitude and the shape to change. So what we have is, as winds increase, wave breaking intensifies, we're able to extract larger and larger droplets into the flow. This is new physics that we hope is more relevant for the process. When we integrate these sea spray generation functions, we get the total mass flux of spray that's given to the air. Showing here that total mass flux as a function of 10-meter wind speed for this wave-based model and for the wind-based model. So we can see there's very different dependencies. And if we look at the same information on a log scale, we can see there's changes in both the sort of lower and higher winds. At about 20 meters per second, the Seastate-based model predicts an order of magnitude lower, 50 meters per second, and an order of magnitude higher. So this is a reflection of the fact that when you use waves versus using wind, you're coming up with fundamentally different scalings to govern the production of spray. And the task is, to sort of keep refining this and figure out how we can get the correct scalings. So that's the spray generation model. We also have to account for the heat fluxes. We use a bulk algorithm for the interfacial latent and sensible heat fluxes, and we model spray processes. So first, we look at generation, as I've just discussed, and then we represent the transport and heat transfer of this population of droplets in the near surface flow. Each spray droplet goes through two important heat transfers. The first we call direct heating. So when spray droplets are ejected from the ocean, they're ejected at the ocean temperature, and that's typically several degrees warmer than the air. These cool down to the air temperature, giving off a heat flux that heats the air directly. The next thing that happens is the droplets evaporate. They start to evaporate. And so this puts moisture into the air, a latent heat flux, but it also extracts sensible heat flux because in order to evaporate, droplets have to get that energy from somewhere, and that comes from the sensible heat of the air. So there's an equal and opposite transfer of latent and sensible heat here. We account for the fact that these spray heat fluxes modify the surface layer temperature and humidity close to the surface, and that feeds back on both the spray and the bulk heat fluxes. And then when we put all that together, we get total heat fluxes that would be sent to the lowest level of an atmospheric model, right? We're going to now take a look at these, but before we do that, we're going to talk sort of qualitatively how do we expect these heat fluxes to behave. It actually really comes down to the droplet size itself. So the time that a droplet spins in the air gives you, controls how much heat they're able to transfer. A small droplet settles very slowly, has a lot of time to transfer heat. Large droplet settles very quickly, doesn't have much time. So this affects the transfers. For the direct heating flux, which is approximately equal to the enthalpy flux from spray, this is a very quick process. The sensible heat exchange is very fast, and so this heat flux works best, is largest when you have large droplets with lots of mass that can quickly heat and give the energy to the air. So 20 meters per second where we have not much mass, this heat flux is small, but as we rise to 40 meters per second or so, heat flux gets very large. The evaporation flux, which is approximately the latent heat flux due to spray, has a different character. Evaporation takes a lot longer than this direct heating. So droplet evaporation requires longer residence times in order to produce high fluxes. And evaporation also depends on the relative humidity of the air. So this works best when you have small droplets and when you have low relative humidity. At these kind of lower wind speeds in a hurricane, where you're away from the eye wall, things are drier, and you're producing smaller droplets, this is fairly effective. But when you move into higher wind speeds in the eye wall, relative humidity is very high, and the droplets are large, so this attenuates this latent heat flux pretty considerably. And then finally, the net sensible heat flux from spray is due to the combination of these two processes. So the direct heating is a positive flux, evaporation produces a negative cooling flux. So you get this very interesting and peculiar behavior where spray can will cool the air within a certain wind regime and then heat the air at higher wind speeds. And I should point out that all three of these heat fluxes are unique relative to one another. They're all different from bulk models. Bulk models have a linear dependence on wind speed. Spray introduces very nonlinear and unique processes. So, expecting the model to behave that way, we wanted to test this and find out what this looks like in realistic tropical cyclone cases. So we took output from 5 coupled model simulations, and we ran that output through this spray parameterization to try and just kind of characterize the range of possibilities. So we took sort of chunks of time from these hurricanes. We chose times in the open ocean, times near land, just to try to characterize the space. The first thing I'll show is spray mass flux. So total mass flux here is a function of wind speed. Each curve represents means of data points collected during one of these intervals. As we can see, spray heat flux is low around 20 meters per second or so, and then it jumps up as we move to higher wind speeds. There's actually 2 families of curves here. Down here, these curves are in the open ocean, and in the open ocean, winds and waves can be fairly well correlated, and so the dissipation that produces spray has kind of the same character as a function of wind speed. But when storms move into shallow water, the waves that they're carrying they interact with the continental shelf, steepen and break more strongly, so you get more dissipation and more spray production at the same nominal wind speed. So this model predicts that when you have this coastal shoaling and breaking, you're going to produce much more spray, which has an impact on the heat fluxes. If we look at the heat fluxes, first this enthalpy flux due to direct heating, there's a very similar character to the spray generation. And there's also this kind of two families of curves. In the open ocean, we have heat fluxes like this, and then as we move onshore, the heat fluxes amplify. And for reference, these heat fluxes correspond to 10 to 30% increase in this enthalpy flux at the radius of maximum wind. Looking at the spray latent heat flux, remember, this is governed by the relative humidity. So we see larger values of the heat flux here, kind of at lower wind speeds. And then it's possible to attenuate these curves quite considerably at higher wind speeds. And this attenuation corresponds to the relative humidity increasing. So storm scale changes in relative humidity causes systematic differences in the heat fluxes we're seeing. These heat fluxes correspond also to about 10 to 30% increase in the latent heat flux at the eye wall. And then the last heat flux is the sensible heat flux. We see, as we sort of expected, when evaporation dominates, we have this cooling effect from spray, and when the direct heating dominates, we have this warming effect. And the crossover point for this is about 40 meters per second, which is going to actually turn out to be pretty important dynamically when we look at the storms later on. We can also look at this in terms of transfer coefficients. So if we kind of normalize these fluxes, calculate transfer coefficients, I'm showing here coefficients for sensible heat, for latent heat, and for total enthalpy. The black lines are coefficients without sea spray. Green lines are coefficients with the Seastate-Dependent spray. And then purple is using the wind-dependent spray model. The solid curves are means of these model grid points, and the shading is plus or minus 1 standard deviation. So these also show that when we include spray, there's a noticeable and meaningful change in these heat transfer coefficients, especially for the sensible heat flux. And something that's particularly interesting and important, I think, is the Seastate-Dependent model predicts a rise in the enthalpy transfer coefficient at high winds, which has been shown in many ways to be an important factor in the intensification of storms and spray's potential impact. So to summarize this part, wind and sea state-based spray generation differ strongly, especially during coastal interaction with wave shoaling. Spray heat fluxes have unique effects, and importantly, spray causes cooling when the 10-meter wind speed is less than about 40 meters per second. It causes warming at higher wind speeds. And then wave-based spray generation predicts a rise in this enthalpy transfer coefficient when the wind speed exceeds about 30 meters per second. All right, so we'll carry that forward as we look at part 2, which is what happens to the actual storm system. So for this, we're looking to see how do these heat fluxes that how does this new model behave? What are the effects on TC structure and intensity? The first thing we're going to do is talk about what we expect. How does this intensification occur in general, and how is spray going to change it? So here we have a cross-section of a hurricane, right? Sort of the right side of the hurricane. We have the eye here in the center line, eye wall, rain bands, the cirrus shield at upper levels, and then the boundary layer. The energetics of the storm intensification are governed by an energetic cycle that moves through the secondary circulation of the storm. This secondary flow includes inflow in the boundary layer, upward motion in the eye wall and in rain bands, outflow at upper levels, and also a component of subsidence down into the eye. Energetically, enthalpy is transferred from the ocean to the atmosphere into the boundary layer. This enthalpy moves inward in the boundary layer, rises in the eye wall in convection, and this convection forces subsidence in the eye. And when this air moves down in the eye, it's compressed, it warms, decreases the central pressure, and continues the intensification cycle. So how is spray going to affect this? Well, the first thing that's going to happen is spray is going to change directly the heat fluxes. We've just looked at that, changes moisture fluxes, changes the heating. So it changes the fuel, quote unquote. But when spray enters this coupled system, it's also going to change the structure of the storm. We expect it to do so in meaningful ways due to the fact that we have these large changes to what will end up being the buoyancy flux. At lower wind speeds, we expect spray to have a dominant cooling effect. So we expect cooling in the boundary layer. And then as the storm intensifies, we expect to start getting warming under the eye wall as we reach higher intensities. So these changes together, changes to the structure, changes to the fuel, are how we expect spray to affect the storms. To investigate this, we ran coupled model simulations with spray physics included in the flux calculations. We ran simulations with spray, without spray for 4 hurricanes and compared the results. First, I'm showing you results from Hurricane Dorian. This is minimum sea level pressure over 5 days of storm intensification. The simulation without spray is blue and the simulation with spray is red. For the first 4 days of this simulation, the intensity with spray is actually less than the intensity without spray. The spray is actually is holding back the intensification of this storm. Then these curves cross, and there's another day during the period of maximum intensity where spray actually strengthens the storm. And this is a very interesting and sort of subtle and complex result. What we found looking through this is that it comes down simply to spray cooling suppresses eye wall deep convection and intensification, and spray warming promotes eye wall deep convection and intensification. We divided this up into 3 stages of effect. And to kind of describe this, I'm also showing a Hav-Mahler style azimuthal mean plot of the spray sensible heat flux, showing the warming and the cooling. The radius of maximum wind is here in this dashed line. We define stage 1 as the period where the spray sensible heat flux is negative everywhere in the storm. So spray is cooling the storm at all radii. And in this storm, it occupies a period of about almost 2 days. During this period, the storm with spray is weaker than the storm without spray. The second stage starts when spray begins to warm underneath the eye wall. We reach 40 meters per second under the eye wall. We start to get positive spray heat fluxes. We expect this to cause intensification, to invigorate deep convection, but this second stage actually continues for, in this case, over 2 days before the storm actually becomes more intense. So we sort of call this the comeback stage. It takes a while, but this warming has begun to act, but it's still being opposed by the cooling that's happening outside in the boundary layer. And then finally, the third stage, when spray finally overcomes this inefficiency, makes the storm stronger, we're calling this stage 3. This corresponds to continuing heating and even further heating under the eye wall. And this is sort of the process that we've deduced. We looked at this using 4 different hurricanes, Dorian, Florence, Michael, and Harvey, which occupied a wide range of sizes, evolutions, and intensities. And we found a consistent response that these 3 stages are present in which spray initially opposes intensification, followed by a period where it may promote intensification if the storm on its own can reach an intensity to allow it. I'm going to kind of briefly go through some of the structural changes that are associated with this. The first is how spray changes the boundary layer itself. This is an azimuthal mean cross-section of theta V, so virtual potential temperature, which corresponds to the buoyancy. This is during stage 1 where we're cooling all the time, right? So down here we have the boundary layer height. What's being shown is with spray minus no spray, so theta V is less when it's blue. And when we're cooling, we do indeed see this decrease in buoyancy throughout the boundary layer. Mixing distributes this change in buoyancy throughout the boundary layer, and all that moves inward into the core. But there's also additional structural changes that get started during this stage. I'm going to show this for a period during stage 2 for Hurricane Florence, where it's sort of developed more. What I'm showing here is radial wind speeds without spray and with spray. What I want to look right here is the structure of this outflow jet. So above the boundary layer, it's common to see an outflow jet of air that's moving outward. And the structure of this changes depending on the presence of spray. When spray is present, the structure of this jet is more shallow and elongated, which we can also see here in this sort of red-blue dipole. So spray is changing the structure of this jet, and we found that this corresponds to changes in the transport of enthalpy or moist static energy within the storm. So this is that same period during stage 2, difference plot of theta E, equivalent potential temperature. So we're basically showing the enthalpy for convection. I've also got here the outlines of the strongest upward motion in the eye wall. And what we find is during stage 2, even though spray is warming underneath the eye wall, there's a deficit of theta E at the top of convection, suggesting that the enthalpy coming from the surface is not rising as effectively in convection, and thus we have decreased intensity. But there's also a region out here over this boundary layer outflow that has a surplus of theta E. So this is suggesting to us that the presence of spray in the boundary layer, even though we're not changing the enthalpy flux, it's causing structural changes that cause enthalpy to rise less efficiently in the eye wall and to be sort of kind of lost and spilled out in this outflow jet. When we move on to stage 3, where spray has kind of overcome this inefficiency, we see that that this has been compensated. So there's a surplus of theta E, there's more convection moving upwards, but there's also additional higher theta E outside of this, the sort of downstream of this boundary layer jet. So spray is continuing to be inefficient in the structure, but that's been overcome by just finally having enough total enthalpy and warming under the eye wall to to compensate. So in summary, the effects on storm intensity can kind of be summarized as follows. In stage 1, which corresponds roughly to tropical storm in category 1, spray evaporation cools the boundary layer. This suppresses convection, causes cooler eye, storm is less intense. In stage 2, we start to get warming by spray under the eye wall, but the inefficiency caused by the cooler boundary layer inflow and the changes to the structure kind of overcompensate for this, and the net effect is spray weakening storms. Finally, in stage 3, heating under the eye wall due to increased dissipation, wave dissipation and heating, finally overcome this inefficiency. We get invigorated convection, eye wall contraction, and stronger storm. Okay, so that's what we found as the effects of spray on the storm. And then finally, part 3, we're going to look for a signal of spray in high wind direct covariance flux observations. So during my postdoc, I've gone to Hui and I've been able to get a hold of a large set of data for these covariant fluxes, and I wanted to actually see if we can sort of discern a signal of this in the data. Kind of to go back to this slide from the beginning, I want to just highlight the fact that air-sea flux algorithms based on Monod-Nabokov theory have these forms for the sensible and latent heat fluxes. And you may recognize that these forms are very similar between latent and sensible heat. This is due to the fact that both being scalars, heat and moisture are commonly assumed to behave in the same way as they're responding to turbulence. So it's actually very common to set the sensible and latent heat transfer coefficients equal, assuming that they interact with turbulence in the same way. What we wanted to do was take a look at the observations and see if this holds true or if there's some deviation possibly due to some other process, meaning spray. So, got a large set of direct covariance flux data. A lot of this is maintained by the Ocean Observatories Initiative, which maintains these kind of global long-term stations at key sites around the world. We use data from the Erminger Sea Array, the Coastal Pioneer Array, the Endurance Array, and the Southern Ocean Array. And we supplemented this with some select data from important field campaigns. So Climode, Spurs 1 and 2, and Dynamo. The instruments that give us these direct heat fluxes, first, there's a sonic anemometer that provides the direct covariant momentum flux. It also provides sonic buoyancy flux, which can be used to estimate the sensible heat flux. Second instrument that we need is infrared gas analyzer. This gives you the moisture flux or the latent heat flux. This doesn't get sort of taken out and used as often as the sonic anemometer. The data that we used was 20-minute averages reported hourly. And when we kind of clean the values, we end up with over 50,000 data points of momentum flux, 20,000 for sensible heat, and 17,000 for latent heat. But since it's harder to get these latent heat flux measurements, they don't go out as often, most of the latent heat flux measurements are not in the high wind range. So here's the data. On the top, we have the sensible heat transfer coefficient. The bottom, we have the latent heat transfer coefficient. All these gray values are the individual data points. The blue circles are the medians of the bin data at 1 meter per second intervals. And the red line is the core 3.6 algorithm. The core algorithm assumes the same coefficients for sensible and latent heat. So those are the same curve. If we look at this data, we can see some systematic differences at sort of low and moderate winds, which is not the subject of today's talk. But what we really want to look at is the behavior in high winds. The latent heat flux data, even though there's very little beyond 20 meters per second, show sort of moving steady or kind of rising a little bit with wind speed. And that kind of maintains with what the parameterization is giving. But if we look up at sensible heat flux, there's a systematic drop in these data values as we get past about 15 meters per second. So this is suggesting from the data that these transfer coefficients are not actually equal. There's some other piece of physics that's causing a difference in the real observations. And of course, we now know to expect this could this be a spray effect? If we remember sort of from before, the behavior of the sensible heat fluxes, we can cover up the data range that we don't have, which is most of the interesting area. But what we do see is that up to 30 meters per second, we should expect a decrease in the sensible heat flux relative to the latent heat flux in the presence of spray. If we, we calculated what we think the spray sensible and latent heat fluxes should be for these measurements, and we do indeed see a decrease in the sensible heat flux due to spray, a negative spray sensible heat flux, a positive latent heat flux. And when we sort of roll that into the calculation with core, we find that, so the green is the calculations with spray, medians of all the data values. We find that the heat fluxes with, latent heat flux with spray stays within the range of the data, and the sensible heat coefficient with spray is now brought down and is within the data range. So, and this is without additional tuning of the spray model. So it's very encouraging that we're actually getting behavior that's corresponding with what's showing in observations. This work is ongoing, and we're trying to come up with ways to kind of tune both of these together to correct the algorithm in sort of the low and moderate wind speeds. But we're very encouraged by the fact that we're actually seeing a signal that can be attributed to spray in observations. So to summarize this last part, interfacial-only physics do not seem sufficient for representing heat fluxes in high winds. When we include spray physics into the core algorithm, we anticipate an improvement in these heat flux predictions. And then finally, these heat fluxes are still very scarce and very hard to get, especially the latent heat fluxes. But they're critical for calibrating these models. And OOI sites, like where we got a bunch of data from, are very well suited for augmentation with these systems to continue to get these important measurements. So that's something that we're kind of pursuing going forward. Finally, to kind of just summarize everything, the conclusions of the work that I just showed you are that Seastate-dependent spray heat fluxes have very complex dependencies on waves and thermodynamics, and their behavior is very different from previous wind-based approaches, as well as to bulk algorithms. When we introduce spray in the coupled system, we see competing effects on hurricane intensity that produce systematic influence on the hurricane life cycle. The net effect of spray enthalpy is to increase intensity eventually, but spray evaporation provides a process that affects hurricane intensity without directly changing the surface enthalpy flux. Next, spray effects appear to be present in currently available observations, which is encouraging, but more work is needed for that. I would also like to highlight that coupled atmosphere wave ocean modeling is very important for capturing these effects, including the sea-state dependence. And I also have these, so if you're interested, I also have these subroutines out on Fortran, and am very interested in collaborations if anyone is, has been interested by this and wants to kind of ask your own questions. And then just one last thing, where's the community headed in high winds? There's a lot of work to be done, especially on the high wind flux processes. So we only discussed spray heat fluxes, but there's also issues of spray momentum effects, changes in steady state and high winds, airflow separation and changes due to wave drag, bubbles, turbulence, and coastal interactions. So the community is hard at work looking at these processes individually, how to understand them, observe them, and parameterize them. The next thing is that we really need new observations in high winds. As you can see, we're very data poor, especially for these really precise interface processes, and we need to measure all the relevant variables. Fortunately, we're at this kind of new age of autonomous vehicles here with sail drones, air drones, gliders, and these show great promise to get observations we need, especially when coordinated with ships, aircrafts, and buoys, as kind of the community and especially the hurricane community is doing. Next, coupled atmosphere wave ocean modeling is very important and is in development. And it seems that kind of iterative development between model developers, observationalists, parameterization builders is going to be really important in order to nail down these physical processes and make them work in models. And then finally, it's going to be real great when we're able to take this information and these models and give them to the community to allow engagement of the scientist community in these high wind issues. So I think that the development of open source, community-facing code and data is going to really help foster collaboration and get to work on these really important high wind issues. So that's everything I have. Thanks for your attention. I'd be happy to answer questions.
All right, thank you. That was great. Plenty of time for questions.
I'll begin. Great presentation. I learned a lot. It seems, all of this flux seems to depend on the difference between those sea surface temperature and the air temperature, correct? Do you see a change in the results depending on how different the sea surface and air temperatures are?
Well, certainly when we look at the sort of the family of tropical cyclones, they all have different interactions with the ocean. And so that dependency is definitely a part of it. And as you move to warmer waters, you should get stronger, you should increase both the sensible and the latent heat flux from spray, I think. I think it's also interesting to think about moving to an extratropical situation where the air sea temperature difference is different, but the sea surface temperature is also much lower. So your evaporation, so your humidity and evaporation physics are going to be a little different too.
Yeah, you could actually envision the opposite case where the ocean water is a lot colder than
Exactly.
the air, right?
Yeah.
And look at those kinds of impacts.
Yes.
Thank you.
Early in your talk, you showed a difference when the open ocean versus a coastal regime. I was curious, where in your model does that come from, or does it come from the wave field?
So so you may be talking about this right here.
Yeah.
Right?
Yeah.
So so the wave model provides the dissipation, provides all the wave properties. The wave field evolves in the wave model. That provides properties including the dissipation. When that hurricane moves over the shelf, then the wave model naturally produces higher dissipation.
Okay, so
Yeah.
it's the wave field that's
Yeah.
doing that.
So the spray algorithm doesn't have anything internally
Yeah, okay,
that
all right.
adjusts for that.
I'm not a hurricane person, so maybe my question is not kind of appropriate. But I think there have been studies in the past looking at the effects of sea spray on the hurricane behavior. So you provided a very nice explanation of the simulations, although I have to say the impact was kind of not great. I mean, we like to see kind of a big effects. The effects was relatively minor. And I was actually worried to interact you asking whether that's an ensemble or just one simulation. But then you get couple simulations, different storms, so that kind of takes this question out. But still, historically, people look at the impact of spray in hurricane simulations. So how your picture fits into those previous studies.
Yeah, so that's right. So there have been studies over the years, and a lot of them find like a tremendous impact of spray. So there's so much uncertainty in the parameterizations from 30 years ago to now that I think the history and the literature demonstrates the wide range of possibilities that you can get just based on the uncertainty. And there have been different assumptions made about how to treat spray physics. In some cases, even based on the idea that it's just the total enthalpy flux that matters, we don't actually need to address the evaporation, right? So if I had left evaporation out of this, looked at just at a total enthalpy kind of thing, we probably would have gotten a stronger response because we wouldn't have this evaporative cooling holding it back. And so I think what this result confirms is that the enthalpy is important, but also the sort of enthalpy neutral processes are important. And also that we really need to nail down kind of the magnitudes, especially the spray production. And we've done some sensitivity studies sort of offline looking at changes to the parameters, and there's a pretty strong dependence on the total amount of spray produced, the size, shape of the size distribution. So I think what we've shown here is hopefully kind of like a baseline of the physics in this model, in the coupled system, in the processes that we think we can understand. And from there, the task is going to be to find out what's the next most important thing to correct using observations or to change in the models.
Okay, I have a quick question, follow-up, since I'm holding the microphone. What about the spatial resolution in some of those simulations? Those are relatively coarse, am I right? Definitely not like, here at NCAR, we've people done like LES of hurricanes. That's nothing like that, am I right? That's kind of a traditional kilometer kind of convection permitting as we used to call it hurricanes. So that's probably, they may have some impact as well, especially when you talk about how boundary layer behaves, am I right? That's the buoyancy flux that affects boundary layer and so on and so forth. So that's another kind of a caveat, if you like.
Yeah, I think you're absolutely right. We were trying to stay in the regional modeling space, kind of thinking towards how this could help an operational model. And so we use bulk wave properties. The highest resolution is like 1.3 kilometers. And so we don't have those things that get resolved better when you go down to LES. There's certainly an opportunity to kind of partner with LES to try and see what we're missing with that. I think that could be a valuable thing moving forward.
Okay, there's an online question. See if I can read it from this angle. Sorry, Chris, I'll lean in a little bit. Very interesting talk. I'm curious about how these processes and interactions are affected by the composition of sea spray. Sea salt, sulfate, organic carbon, virus, etc. Do you envision chemistry part of the coupled system?
Yeah, so yes, I think it does make a difference. There was Vanderplau and Soloviev in Florida did a whole lot of work looking at how surfactants can affect the generation of spray using these sort of CFD crazy droplet breaking simulations, and found that when you change the properties, the molecular properties of the liquid, you get a change in the way the spray is produced. And so that will eventually that affects, I talked about how the size of the droplets matters, so the way they break up matters. And so I think that is definitely a whole nother door to try to go down. And it will be, that's another challenge. I think it's definitely relevant, especially because it affects microphysics, and it's something that that can be addressed later.
Wondering how confident are you in the size distribution of the drops, and is there a way of getting at that with wave tanks or other Do you
So-
have a way to verify
Yeah.
it?
Great question. So one of the things that I think is one of the things that we accomplished with this work was that there was a study in 2016 that came out of the Sustain tank in Miami, where they did wave and wind forcings, they measured size distributions, and they actually showed these peaks, the positions of these peaks as you move up to higher wind speeds. They found that the peak does actually move to larger droplets as you increase in wind speed, in the lab at least. And we use that data to calibrate the model. So I don't know how many clicks I'll have to do to get back there, but so these curves, sorry, I went way too hard. So these curves, the smooth curves, were calibrated to the data that came out of those experiments. And you can certainly show differences between what's happening in the wave tank and what's happening in the field. But I think we did about the best we could with information that's been available. And we're looking into ways to try and actually measure something about the generation rate and the droplet distribution on sail drones and wave gliders and things like that.
What else? All right, I can't help asking this question. There's definitely an analogy here to cloud and rain microphysics. So if you been, I don't know, thinking about that problem in that way, or like looked at some of the literature, I'm thinking in particular things like evaporation of drops, where effects of ventilation are really, really important, but probably a very large uncertainty, things like that, especially since you have relatively large drops as the wind speed goes up. So kind of an open-ended question, but curious about that.
I think it's so a lot of this kind of the spray physics is based on cloud, and it's based on what's been done for clouds. I'm not deeply into the cloud literature, so I haven't like gone down that road deeply, but I think it'll definitely be a useful thing to use in the future. A lot of the instruments that we're trying to kind of think of using for spray are actually basically repurposed cloud probes. So yeah, I think there's a lot that we'll be able to learn.
Yeah,
from
and
that.
to follow on the same theme is that I don't think we really understand well how those particles behave in turbulence, and especially in high turbulence near the sea surface. So whatever we know in cloud physics is typically based with some caveats, with particles that fall through the kind of quiescent air, which is of course completely different here. So, braking, evaporation, all those things, sedimentation, turbulence affects it. So that's definitely the way to kind of think about where cloud physics and the environment that you are thinking of or working with, kind of how they differ, because they differ quite a bit, I'm pretty sure.
Okay, yeah, well, thanks. Thanks for the suggestion.
Okay, one more question from Peter.
I assume those curves are integrated over the whole storm? One of your, go down in your talk just a little bit.
You want me to, like, a different slide?
Yeah. Let's see.
So I have... You're talking about the couple?
Yeah, something like that. Did you see any, did you interrogate the results based on what quadrant they were in? Whether it was on the right side, left side? I would assume the left side, winds and waves are more opposed, there'd be more braking, more spray, not?
So we do, so there's definitely like kind of a left-right asymmetry. Here, I have a kind of a backup slide on that. So this is just kind of a snapshot in the open ocean. One of the storms moving northward. The dissipation is definitely larger on the right side of the storm, where you have higher waves, you have more wind input, so you have more braking. And then when the storm goes on shore, it kind of all bets are off, because it also depends on the bathymetry. So even though we have similar, all right, this thing doesn't work anymore. Oh, it's a mouse now. Okay. So even though we have kind of similar wind speed magnitudes, we have very different structure in the dissipation because of the movement up the shelf. We looked at asymmetries in the heat fluxes, so that there tends to be kind of an asymmetry in that also. And I think, if I remember, the heat fluxes are stronger on the right side where you have more storm, or where you have more spray being generated. But I think looking at the asymmetries, especially in the boundary layer structures, will be a good next step for the work.
Yeah, I was just thinking that if you wanted to show spray effects, integrating over the whole storm is going to kind of gloss over it.
Mhm.
Whereas if you pick out one of the quadrants,
Yeah.
you might see more effect.
Yeah, that's a great idea. Thank you.
Okay, let's take one more question on Slido and then we'll wrap things up. So the question is, I wonder what skill the wave model actually needs to enable this class of spray parameterizations. What I recall is that you rely on bulk wave statistics of the dominant waves and wave bottom interactions to get the shoaling, correct?
Yes, so this model, okay, so the question is, how good does the wave model need to be? So we don't use any spectral wave properties or any like properties of the spectrum in this. And that's kind of intentionally because, I guess we assume that it's simpler at least to try and use these bulk properties. Maybe that's something we can validate a little more easily. And so I think that if the wave model can reproduce those bulk properties, that would be the most important thing right now. It's possible that in the future that we'll be able to actually look at spectral properties of the waves in spray generation, but right now it's just these kind of bulk properties.
Okay, thank you very much. Let's thank Ben one more time.